Hi science friends, today is the last bit of material for this gas unit that we've been working on. So today we are talking about Dalton's law and Graham's law. So Dalton's law deals with partial pressures. So what a partial pressure is sometimes gases mix together and there's lots of different combinations of gases in the whole. So like in our atmosphere, for example, our atmosphere is made up of oxygen, nitrogen, carbon dioxide, and then some other gases too. But those are the three primary gases. And so if we want to know the total pressure of the atmosphere, we add up the partial pressures of the major gases. And that's what Dalton's law of partial pressures tells us. The total pressure is equal to the different parts, okay? Now, it says ... here because it's as many parts as you have. If you have a gas that's a combination of 20 gases, then you would have 20 parts out here. You'd go to P20. If you only have 3 gases, then you'd stop right here. The total is the combination of the parts. And so however many things you have to add together is based on however many different gases you have in that mixture. Okay, so the partial pressure is just the pressure of one piece of the whole, okay? And the whole makes up that total pressure. So let's look at a practice problem together. It says, air contains oxygen, nitrogen, and carbon dioxide and trace amounts, that means small amounts, of other gases. What is the partial pressure of oxygen? So that's what we're trying to find. At 101.3 kPa of total pressure. So that's our total. So I'm going to go ahead and write it on the left because the total here appears on the left. 101.3 kPa is our P total. If the partial pressure of nitrogen, carbon dioxide, and other gases are 79.1, 0.04, and 0.94 respectively. So basically what that means respectively is we listed them in the order that it said in the question. So nitrogen is 79.1, carbon dioxide is 0.04, and other gases is 0.94, okay? And we are trying to find the partial pressure of oxygen. So that's what we don't know, partial pressure of oxygen. So I'm going to write that in as my variable. We know that the nitrogen is 79.1. So I'm going to write that, 79.1 kPa. The carbon dioxide is 0.04. kPa. And the other gases is 0.94 kPa. Okay? And so basically all we have to do is solve for O2. And so you're going to add these numbers up and subtract them from 101.3 kPa. Let me grab my calculator here. And of course it's dead. Okay, so let's see if I can do some long math here. So 79.1, y'all have your calculators in front of you, but I don't. So 0.04, 0.94. So we've got 79 point, I'm just really struggling this morning. 79.8 minus 101.3. So is that 21.32? Okay, I'm thinking that's what it is. Doing mental math here is going to be the partial pressure of oxygen. Okay. Partial pressure of oxygen. Now, if I've messed up the math there, y'all fix me, but you see what we've done here, okay? So I have one for you to try on your own. All right, so you try this one, and then I will be right back with you in just a moment to go through it. And so I think what you should have gotten here is 93.4 kPas, okay? 93.4 kPa. And you just add up the parts. So we wanted the total pressure, and so the parts were 20, 46.7, and 26.7, and so when you add those up, you get 93.4 kPa, okay? Now, I will say, sometimes in your assignment, these are pretty easy problems. Sometimes in your assignment, you may have kind of a two-step problem where you have to use one of the other gas laws. Maybe you have to use P1 V1 equals P2 V2 and solve for this pressure before you could put it into an equation like this. So some of your problems may be more of a two-step type problem. So be on the lookout for things like those. And of course, if you need help, let me know, okay? So that is Dalton's law of partial pressure. The last thing I want to talk about is Graham's law. And so Graham's law is the law of effusion. And so let's talk about first what the terms diffusion and effusion mean. So you've probably heard of the term diffusion. So I'm sitting in my kitchen right now, and I have a little thing from Bath & Body Works, a wallflower that's got, scented stuff that comes out of it, makes my house smell Christmassy. And so right there in that little wallflower, the scent is very concentrated, right? But as it comes out of this thing and that's plugged into the wall, the scent diffuses across the room, right? It moves from an area of high concentration to an area of low concentration until it's uniform throughout the space. That's what diffusion is. Gas particles diffuse. And so when it comes out, it's just a tiny gas particle, or maybe even liquid particle suspended in a gas particle, but it spreads out into the space. And that's what diffusion is, okay? Now, effusion is slightly different. It's still spreading out into a space, but more than that, it's escaping through a tiny hole in the container. It's escaping through a tiny hole in the container. And what Graham's law of effusion tells us is that gases effuse proportionally to their molar mass, okay? So if we're looking at two gases and we are trying to see their rate of effusion, we have to look at the molar masses of them. So when we do Graham's law calculations, we're always going to be comparing two different gases, okay? Now, the thing that's slightly tricky about Graham's law, and what people always mess up with it, is A and B are representative of the gases that we're talking about. So maybe we say oxygen is A, nitrogen is B. I always like to write that down when I do these problems. But notice over here that the A's and B's are flipped, okay? And people mess that up. They will do it rate of A equals the square root, that's a square root sign, of the molar mass of A, but it's not. This is flipped. If this is A, up here on top is B, and this is B, up here on top it's A, because it's inversely proportional, and inversely implies that we're going to have to flip it, okay? So let's look at a problem to practice this, and I didn't give you very many of these problems. I'm not sure why I didn't on our practice, so I apologize for that, but you have some to practice today. So which gas diffuses faster, helium or nitrogen? So first we have to remember that helium and then nitrogen is a Hofbrinkel. So when we do nitrogen, it's got to be a Hofbrinkel. So we're going to call helium A and nitrogen B, okay? So let's look back at our formula. The rate of A equals the rate of B over the molar mass of A and the molar mass of B, okay? So we'll say the rate of helium over the rate of nitrogen. That's how I like to set them up, okay? Call those your gases down there at the bottom. Substitute in that A and B with your gases, okay? Now we're going to add in our square roots. I can't forget that part. Now what we have to know is the molar mass. So all we have to do here is add up the molar mass of A and the molar mass of B. Well, helium has a mass of 2, okay? And so it's going to go on the bottom. It's going to be 2, the square root of 2. And nitrogen is N2. It has a molar mass of 28. And so you're going to put it there. Notice that I crisscrossed them. Nitrogen went up top and helium went down below. They swapped places, okay? That's important. You can't get it right the other way. So if I put this in my calculator, the square root of 28 is 5.29, okay? And the square root of 2 is 1.41. So then 5.29 divided by 1.41 is 3.75, okay? Now this doesn't have a unit on it because it's a ratio. And so what this means is the one on top is that much faster than the one on the bottom. So helium diffuses 3.75 times faster than nitrogen. Okay? And that's what Graham's law tells us. Okay? Now, had you have not been able or not been asked to say how much faster, you could have just looked at the molar masses of those elements and said helium, okay? And sometimes that may be the case. If it doesn't ask you how many times and you don't have to do this step, you can just say, oh, well, helium weighs 2, nitrogen weighs 28, and so helium is going to diffuse faster. Done. But since it asks us how many times faster, then we have to do this step, okay? So that is it for your new material. That is it for your lesson today. If you have any questions, then let me know. And if not, then you all have a great day.